This week we're going to talk about electric motors. And before we get started, let's revisit some of the basics. Remember, we talked about electromagnetism. Electromagnetism plays a big role in motor operation. So we know that anytime a conductor is carrying current, that these lines of magnetic flux or magnetic fields develop around that conductor. And we also know that the stronger this current is, the stronger the magnetic field and the further out these rings of flux develop. Looking at a conductor kind of head on like this right here where the dot is the conductor, and it's passing current through, we see that these rings of flux develop around it. And we also see that over here those rings of flux are going downward, over here those rings of flux are going upward, and because of that, this half is opposite this half in magnetic polarity, as you can see here. So if we kind of draw those magnets in, you can see that the top half of the conductor is a magnet of one polarity, while the bottom half of the conductor is a magnet of the opposite polarity. And combining those together, you would see that you essentially have this electric field, this electromagnetic field, develop around that forms electromagnet. Now, if we were to place this magnet in between magnetic poles, here's a north magnetic pole, here's a south magnetic pole, we see the lines of flux going between these. Now, because this is north and this is south, the tendency is for this to be attracted to this. The north and south are going to attract, but because they're fixed in a permanent position, they can't. So that tension, that magnetic tension that exists between these, we've illustrated here with these lines of flux. Now, imagine that we have another magnet inside the lines of flux of this larger magnet. You know that these forces, these magnetic forces, are going to act upon this magnetic. Those magnetic forces of this magnet are going to interact with these other magnetic forces, and because of that, you're going to get movement or a tendency to move. So on this top part of the conductor, the interaction is a tendency to push down on this conductor. In other words, the top part of this conductor is being repelled by these lines of flux, but on the bottom side, it's being attracted. So both of these forces are equal, and then they're the same direction. So the tendency is for this conductor, when it's creating a magnetic field around it, in the presence of another magnetic field, it has a tendency to want to move this direction. And you know, anytime you put magnets in proximity of one another, you feel that force that's wanting to cause movement to occur. Here's a representation also. This would represent the electromagnet, the currents going in and creating this polarity, north and south. You can see it's being attracted on this end, while it's being repelled on this end. So in the armature, the rotating part of the motor, we have that electromagnet. We have coils of wire and we have steel. Typically we have steel, laminated steel in the armature, and we wrap coils of wire around it and run current through it to make an electromagnet. And in doing that, we situate that in the middle of north and south poles that are in the outer side of the motor, and that force, those forces that are in play, want to create that movement. But how do we get the current into the windings? Because if you think about it, if we just had all those windings and we had wires attached to them and we ran them outside of the motor and hooked them up to a battery or a power source, well, as soon as the motor would start to turn, those wires would tangle up and break. So that's not going to work. So the way that we do it is like this. We use commutators and brushes. Commutators are segments of copper, and one commutator is hooked to one end of a winding, and another commutator is hooked to the other end of the winding. so that if I can put current into this commutator, it goes into the winding, it flows around however many loops it has, comes out the other commutator, and can go out to the real world. So in this case, I have this commutator contacting this brush, which is electrically conductive, and it's connected to my external power source. The external power source lets current come into this brush. The brush conducts it onto the armature through this commutator. The coil runs through the winding. It comes out on another commutator segment into the brush, and I've got my loop. This goes to the other side of my power supply. These springs are there to exert constant tension because this is rotating. There's a tendency for this to bounce around a little bit. So the springs help hold that tight against this. And especially because this is carbon, this will start to wear. Brushes will start to wear down, and the gap that would develop would have to be compensated for, and the spring does that. It keeps constant pressure on this so that as the brushes wear, there's still adequate contact here on this surface. And you can see how they've labeled these as the commutator segment. There's the actual rotor or armature shaft, insulation between the commutators so that they're isolated from one another electrically, the brush itself, spring to provide tension, conductors to the real world. And I think maybe we could take a look how that relates to an actual piece here. This is what the commutator would look like. Now, our example shows only 4 segments, but in reality, we're going to have many because here are those windings. Here's the steel, the laminated steel that these windings are wrapped around, and you can see that there's quite a few windings, and each winding or set of windings, because sometimes we parallel windings, are going to be attached to these commutator segments to receive and pass current to the real world. You can see the brush here, the lead that's coming onto the brush, the spring maintaining constant tension on the brush. You see the shaft that runs through the motor. This particular piece here serves as a fan. As it rotates, it provides airflow across the motor for cooling. Another example how real pieces relate to the schematic symbols and in motion. This illustration shows the external power supply that we're going to use to put current through the winding. So the current leaves the source, comes up, enters the brush onto a commutator segment, goes through the winding, and the flux that develops around this electromagnet interferes with these magnetic fields and causes the rotation. And the circuit's complete through the other commutator segment. And as this rotates, then you're going to see that this particular winding, the blue, is now going to be on top, and it's going to receive power, and the current will flow the same direction, so the motion continues. A DC motor can be either a permanent magnet, where the field poles on the outside of the motor are fixed, or they can be a variable field, where you have electromagnets as your field poles. A permanent magnet motor is very common. We'll take this example to show you how you vary the speed of a permanent magnet motor. A good example of this would be the heater blower in your car. So if we want to change speeds of this, if the power's coming through the fuse up here, and initially let's set this on off, and then if it's in the off position, there's no path connected to this point, so nothing happens. But if I switch this to low, now the current can come in, and I travel down this way. And I enter these blower resistors at the top here, and I travel through the top half of this resistor, and I get to this midpoint, but there's no path that this can go, so that's a dead end. There's nothing connected here, so it has to go the other half. It gets to here, and again, there's no connection, so that's a dead end. So the only option that this current has is to flow from the source through all of these resistors or this total resistor, into the load. And because we're limiting the current, because we've put so much resistance in this circuit, the speed of this is limited. But if I want to go medium now, my current can travel down here to the midway point. Can't go this way, and that's a dead end. It can't go this way, it's a dead. So it gets to the midpoint and goes through half the resistance. By cutting the total circuit resistance in half, I've doubled the current. Consequently, the motor can do more work, and that's evidenced by moving faster. Finally, if I put it in a high position, we see that the resistors are bypassed entirely and the full current is delivered to the motor for maximum speed. Looking a little more inside of a motor, we're seeing here I've got the poles, the field poles. This is not a permanent magnet motor. This is a variable field motor because I have these coils of wire wound around the poles, as you can see here. Here's my windings around steel poles. Here's the windings around the steel poles. It's hard to see the steel poles because all the windings around it. Here's some more down here. You see that this motor has several poles, and that's very common to have multiple poles in a motor. We can control now the current that's going through these to determine the strength of this field and consequently the speed and torque and the power of a motor. Some very huge poles, good size motor here. There's different ways to wire up or configure your fields in relation to the armature. We'll take a couple looks here. This is a shunt motor. So a shunt field, shunt is another word for parallel. So if you hear something about a shunt, we're talking about something that's parallel to something else. So in this case, I have a source, and the same source supplies current for my field. These are my field poles wound around the steel, and my armature. So here's one electromagnet, and here's the other. These are the ones that are the windings inside on the armature. This is what this schematic represents. And these are the windings around the field poles. So both are receiving current from the same source. In this example, we can control how much current is going through this field with this variable resistor, consequently affecting the speed of this motor. In this case, the field current's fixed, but I'm controlling the armature current with this variable resistor, and that's going to limit the amount of magnetism that this creates, and thereby limiting the amount of torque and forces, opposing and interacting forces within the motor and the speed. Here is a starting circuit, typical starting circuit of a motor. Let's take a look at this. Here's my line. This is my line coming in, and I've got a switch. This dotted line, if you recall, represents mechanical coupling. So whenever one of these switches are thrown, this disconnect, they're both acting in tandem. So we put power on, and that supplies current through this circuit here, this rung of this diagram. And it looks to me like current's going to flow. It's going to be limited a little bit by this variable resistor. They're calling it a rheostat. It's probably a very good size variable resistor. But initially, now that I look a little closer at that, unless RA2-2 is picked up, we're going around that resistor. So we'll look further into that to see what that is. MS1, if MS is not picked up, then I've got nothing going on here. I've got a thermal overload as the current would become excessive in this circuit, in the armature circuit. If the current became excessive, this would heat up. It's made out of bimetal strips, and that heat would curl and would cause overloads to open up and break. Actually would trip this set of contacts right here. We'll keep that in mind too. And here's the armature. It's represented that there is some resistance in the windings, and it also represents counter EMF, counter electromotive force, which we'll talk about in a little greater detail. But essentially, whenever you're trying to use a motor, it also is acting like a generator, and that's what this DC power symbol represents. At the same time, conversely, anytime you're trying to use a generator, it's trying to act like a motor. We'll talk about that later too. Interpole windings are there to reduce sparking, commutator sparking, but we're not going to worry about that for now. And here I have a resistor. Resistor has some contacts, but right now we're going to assume that none of these are picked up. So overloads should be okay because there's not been any current flowing to heat these up. So we're going to say those are normally closed, and they are closed. The stop switch is normally closed, and this is open, so this is dropped out. Down here, this is a timer. This is a time close. So once this picks up, this will time, and it'll close, and when it does, it'll pick up this relay coil, and when that relay coil picks up, energizes, it's going to start this timer, and when this times out, it's going to close and pick up RA2. Right now, nothing's happening. I push the push button. Current flows this way, energizes or picks up MS, which causes this set of contacts to close, and this, MS1 and MS2, both close. So MS2 closes, which seals in the push button so I don't have to keep holding it in, and this gets current flowing. Well, RA1 and RA2, neither one are picked up yet because they're timing out. So initially the current has to run through both of these resistors. This limits startup current. The startup current of motors are high. We talked about that last week. We talked about sequencing motors so that you don't have several motors starting at once and have this huge inrush current. Not only can you trip breakers with this inrush current, but it also can produce an awful lot of torque. So you don't want to break shafts or anything else because of the sudden torque that you've created. This starts the current off a little slow. Up here, RA2 is still not picked up yet. It's still timing out. So this is still closed, and the current is going around that, so that I'm getting maximum field current at this point. Now, after this does time out, the timer started when this closed. Once this times out, I don't know, 5 seconds or maybe not even that long, that closes and causes RA1 to pick up, which causes this to start timing. But also what it does is it closes this set of contacts. So now the current that was coming in and having to go through both of these, now they come in and goes through, bypasses this one. And just like in our blower speed demonstration or example, now we know that that motor is going to increase in speed because of the increase in current. Then once this times out here, it closes RA2, and we're going to bypass both of these resistors, allowing full current to go through the armature. Also, this is going to open up, forcing the current to go through this resistor that's variable, and I can do greater adjustment of the motor speed by using this resistor. Here is an example of a DC motor. We'll just take a quick look at this. Right now, I've got a stop button that's normally closed, but if I hit forward, I pick up CR1, it seals in so I can let go. This contact closes, and the current goes through. This is actually, I think, a simpler circuit than the one we just looked at, so maybe study that a little bit too. This is a reversing circuit. So now we've decided we want to do something a little more, and it's going to take, we want the motor to reverse now, so it's going to take a little more circuitry to accomplish that task. And the way it works, I've got a fixed field as I did the first time, but I have buttons here for forward and reverse. So if I hit forward, R is not picked up because that only picks up when I want to go in reverse. And these are my electrical interlocks, like what we talked about last week. We were talking about the garage door opener. This is another example. I can't get this motor trying to go, well, let's look while we have this. It's not just a matter of trying to get the motor to go two different directions at one time, because it won't. Here's what will happen. If these weren't in here and somehow I energized CRF and CRR at the same time, forward and reverse, what would happen was these F's would close and these R's would close, which would create a dead short across the power supply. So to avoid that, I have these electrical interlocks, and the only time that if I pick up forward, this is going to open up, so there's no way that R can ever close. This can never pick up until this drops out and allows that to close back again. So I push the forward button, this picks up, and this seals it in, and my F contacts close, which allows the current to flow this way. It can't go that way, that's a dead end. Flow from A1 to A2, and then out, back around. So my path is like that. And it's sealed in. It's going to stay running until I hit the stop button. That's going to stop the current flow into this relay, and it'll drop out or de-energize. Now if I want to go the opposite direction, reverse, I'll hit the reverse button, and it seals in, opens this up so that it can't go, so that F can't close. And now the current can't go this way now, but it can go this way. And the current flows from A2 to A1 in my loop. So if the current is flowing through the windings in the opposite direction, that means that the lines of flux are being generated in the opposite direction, and that the electromagnet that's being created is of an opposite polarity than before, which causes the rotation to occur in the opposite direction. In this example, we're looking at variable speed configuration. I have a fixed field current, and I have my start button that picks up CR1, seals in, and picks this up, allowing current to flow through the armature. I can control armature current with this variable resistor. The more resistance I cut out or reduce, then the more current can go into the load, and the faster this goes, because the magnetic field, the electromagnet in this, is stronger, and it has more force in trying to move away or be attracted to the field poles. This is variable speed setup. Let's take a look at what's going on here. Initially, CR1 and CR2 are both de-energized, so that this set of contacts is closed, passing current around this resistor. This is open, and these two are open. But once I hit start and CR1 picks up or energizes, it seals in here, and it also closes this set of contacts. This allows current to flow from this direction, can't go that way, through this resistor, through this tap. So I can regulate the amount of current flow a little bit with this adjustment. I can vary the speed with this by varying the armature current. But if I want to go into fast mode and I push this, CR2 energizes and seals in, then here, this is going to close, allow me to bypass this. So all full current is now going through the armature. Up here, this opens up, and where this resistor was bypassed, now I'm able to control the field current with this variable resistor. Now, we haven't talked much about this at this point, but I'm going to bring this to you now. It's a little bit counterintuitive, but the stronger the field, the slower the motor runs. And if we reduce the field strength then the motor will start to increase speed. This is somewhat counterintuitive because, wait, it takes the magnetic force of the field in interaction with the magnetic force of the armature. So why, if we take one of those, start reducing one of those, why does the motor get faster? And it has to do with that counter electromotive force, the counter EMF that we talked about, where a motor is trying to act like a generator and a generator tries to act like a motor. So the fact of the matter is, when this motor starts churning, I have my field that's producing magnetic lines of flux, and I have the armature windings that are cutting these lines of flux. And if I'm cutting lines of flux, I'm inducing a voltage, and I'm basically generating current in these windings. Even though I've got current running in, I'm also inducing voltage that causes the current to want to move this way. So in other words, the voltage is being generated by these windings cutting lines of flux are the opposite direction of what I'm trying to impose upon it. So the counter EMF, this counter voltage that's generated inside of this, opposes this voltage. So consequently, the current results from this amount of voltage and this amount of voltage pushing back. So the current starts to reduce. But if I cut these lines of flux, then the generated voltage will go down. And if the generated voltage goes down, more current will flow, again, making this stronger magnetic field and causing the motor to accelerate. So we initially, when we start a motor like this, typically what we do is we start out by getting it up to its base speed. That's what we call it. We get it up to its base speed by using the armature current, controlling the armature current. Once we have it up at its base operating speed, we further can adjust the speed by regulating the field current. Again, lowering the current causes increases in motor speed. What about stopping a motor? How do we stop a motor? Well, obviously we can just kill the power, and in that case the motor will just slow down from its initial RPM. Obviously that's going to take a long time. There's a lot of inertia in that armature that's rotating, so for it to coast will take quite a bit of time. Along this axis is time, this axis is RPM. We also have a process called plugging. You can see that it's very dramatic and drastic. Plugging is actually where we try to make the motor run the opposite direction. So we've got it running forward, we kill that circuit, but now instead of letting it coast, we actually try to run it the opposite way. And that slows it down. As it's trying to reverse direction, it'll do that pretty rapidly. And I don't know, maybe you've done this with an electric golf cart or something like that. You don't want to do it with your car, slam it into reverse as you're going forward because you'll tear out your transmission. But in electrical circuits where you're coupled by magnetic flux, although the torque can be high, many situations, cranes for example, many cranes do this for a way to slow down and stop, is to try to run it backwards. Dynamic braking is where we use the inertia of this coasting, what's normally coasting motor that doesn't have power on it. We now use it as a generator, and we use the counter torque that's developed in a generator, which we'll talk about here in a little bit, to slow it down. And we also have mechanical brakes. Here we see a drum brake. Here are the shoes off to the side. This drum's attached to the shaft. Over here's your motor. So you've got a shaft on one end of the motor that drives your load, pulleys, rolls, conveyors, whatever's over here. And on the other end of the motor, another shaft extends where we can put a brake. This brake is electrically operated. This is the solenoid. So whenever I put power on this, the electromagnet in this causes this brake mechanism to clamp down on the drum. There's another example here. You see a gearbox and a motor This is probably the gearbox because it looks like I've got an oil filler here. So here's the motor, here's the gearbox, and in between them we've attached the brake. This is a close-up of disc. One of the problems, however, with using mechanical brakes is that they wear. You have to change the shoes periodically. They also create dust from the wear of the shoes. They create heat as this friction builds into heat, and it heats the ambient air, causes the air to warm up. So then you have to pay for air conditioning or things like that if the temperature gets too high. And there's wear. These things just wear out, so it needs replacement. That's downtime while maintenance is done to replace brakes. So mechanical brakes are effective and they're reasonably inexpensive, but there's definitely some problems in using them. Here's a plugging circuit, and essentially it's just a reversing circuit, so that if I'm going forward, I kill my forward to hit my reverse, and this thing will try to run backwards. So here's a dynamic brake circuit, and we'll talk a little bit about that, but first let's talk a little more about generators. In the case of a generator, as you recall, I've got my field poles, just as I do in a motor, that sit on the outside, around the outside edges of the motor case. And inside I have my windings on the armature. And I'm going to turn those windings with a prime mover, causing those windings to cut the lines of flux that are being created by the field poles. And in doing that, I'm going to induce a voltage into those windings. Okay, so that's how we generate. But just as in the case of a motor trying to work as a generator, as I'm turning that armature in a generator and there's current flowing through those windings, that causes an electromagnetic field to develop around a winding which interacts with the field poles. And that's exactly how a motor works. So you can't get away from using a generator without those same physics that are going on that has this motor effect. And you can't use a motor as a motor without the same physics effects that are present in a generator. So you're always going to have a counter-electric force in a motor, and in a generator you're going to have counter torque. The direction you're trying to turn it is opposed by this counter torque that's created by the motor action that's in a generator. The more current that flows in the generator, the stronger that counter motor force is, counter torque. If you are stoplight, say, in your car, and you have the fan running, you have your lights on, windshield wipers, and the vehicle's idling at a certain speed. And now I turn on something that's a heavy load. Maybe I've got some fog lights. And I turn those on, and that extra current that has to be delivered by the alternator flows through the alternator, which is a generator, and that means there's more counter torque. You're going to evidence that by hearing the engine speed drop down a little bit, because it's harder now for the internal combustion engine to rotate when that counter torque being created by the generator is pulling it down. So we're going to use that in this case. I got CR1 initially is not picked up because it's not picked up here. This is closed. As soon as I hit the start button, CR1 picks up. This closes and this opens up. Current flows this way and it can't flow this way. So full current is being delivered to the motor. Now when I hit stop, here's what happens. This drops out. This opens up, so no power is being delivered to the motor. But because of the inertia of this rotor, this armature, as it's coasting, because of that inertia, if I put this contact on here, now I've got those windings that are spinning under inertia, and the magnetic field up here, that generated voltage is applied to this resistor, and that creates this flow that's flowing around this way. That counter torque slows this motor down because it's the opposite direction that the inertia was taking it. Regenerative braking. This is a way that's similar to the dynamic braking, but even in dynamic brakes, if I look back at this picture, this isn't 100% effective. This is better than mechanical brakes because I'm not wearing out components, but still, the current is flowing through this resistor, creates power in the resistor, and that power is evidenced as heat. And it's pretty much wasted energy. I'm making power that I can't use. In fact, if this heat creates an environmental problem, then I've got to use more energy to compensate, to cool for that. So in this particular case, what I'm doing is I'm taking the generated power like before, but instead of putting it onto a resistive load, I'm actually putting it back into the line. This is a good application for an electric car. I'm going down the highway, my electric car, and I let off of the accelerator, and now instead of applying brakes, which I can still do, friction brakes, but the vehicle's going to slow because I'm going to use that inertia as a generator to not feed back into the line, but to the battery. So this is actually going to recharge my battery. This generator will recharge my battery. So the power that I took from the battery to run my electric car, now when I'm off of the throttle or applying the brakes, I have added generation that's putting that back into those electrons back into the battery. This is the rotor out of a AC motor. It's called a squirrel cage motor, and you kind of see that it looks more like the wheel to me, but and here's the shaft. You see there's no brushes. There's no brushes in an AC motor. And brushes wear out and cause heat and sparking. So brushes in motors can be a problem. If you ever had a power drill or a tool that you had to replace the brushes, or a starter in your car, yeah, if they wear out, you're kind of dead in the water. Just a brief discussion on three-phase power. The power that comes into your house is single phase, but many industrial commercial applications use three-phase power. So in your house, single phase, we'll say phase A here, over a period of time, over a period of this particular waveform, you get just this waveform, one complete rotation, one complete cycle. But in a three-phase power, while this is going on, you had another one that's offset by 120 degrees, and then you have another one that's offset at another 120 degrees. So in that same period, for one cycle of A phase, you have two more peaks of power. So clearly you're getting more power delivered in the same amount of time, and the power's being supplied more smoothly as being just bump, bump, bump. Now we've got bump, bump, bump. So you can see that those pulses of power coming closer together is a more desirable way to deliver power. If it were a motor, for example, if I'm just supplying power in single phase on the tops of my A's, and it's like bump, 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 then the motor is going to start to slow down between those bumps. But here when they're coming bump, 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 now there's less time for the motor to decel, and it's less difficult to get it back up to speed for any momentum it did lose. This is showing each phase, the way this is hooked up, but these are all in the same generator at the power company. It's just that you've got the poles and the armatures isolated from one another, but they're all turning at the same time. And you can see the loads that are attached to each phase. In the real world, these are attached in what we call Y configuration or a delta configuration. You'll learn more about that probably in another class. I'm not going to go into that in this class. The way you calculate the voltage from the line to the neutral is different depending if it is in a Y or a delta. We have phase angles to be concerned with, which we're not going to get in this class either, but you might in a future class. Delta. Inside of a motor, a three-phase motor, you see that I've got one phase set of poles for phase A, a set of poles for phase B, and a separate 4C. Each of these windings are attached to a common neutral, but my lines are those phases. Here's a start circuit. This is called a motor starter. This is what you might find inside of a cubicle that feeds the motor. You've got your line power that comes here at the top, shown here, your contacts, thermal overloads, and the terminals that go out to the motor. 3 phases coming in. 1, 2, 3. 3 phases coming out. T1, T2, T3, T1, T2, T3. And the motor would be on downstream from this, the motor here. So the control circuit is probably 120 volts, even though the power circuit, where the contacts are being operated by this coil, is a 3-phase, maybe 480 volt. So I pick up MS. The overloads are good. There's not a situation. It's called the overloads to kick out. So this picks up and seals in and also closes these contacts that allows each phase to get power. Here is a reversing starter. And to reverse a 3-phase motor, what you have to do is reverse any 2 leads. So I can reverse this one and this one, I can reverse this one and this one, I can reverse this one and this one. Any 2 that I switch around, the motor's going to run the opposite direction. So in a reversing circuit, that's what I'm going to do. Through these relays, I'm going to accomplish the reversal of L1, L2, and L3 at some point. So L2 in this case is staying the same because L2 goes right around. So either forward or reverse, this side of L2 is going over to here. But in the case of F, the difference between F and R is we're switching L1 from here to here, from here to here. And we're switching L3 from here to here, from here to here. So we're switching L1 and L3 through this circuit, forward or reverse, forward or reverse. Overloads will take out either direction. A dual voltage motor in a Y configuration. I have 3-phase coming in, but I can hook these up, that I put these windings in series for high voltage situations, or if I have a low voltage situation. See, this is 480. It's the same motor, but I've hooked these windings up, so 480 is divided by 2 because they're in series. But if I have a 240, I'm still going to put 240 across each winding, but I'm going to have those windings paralleled. And it's just how I hook these wires up, which are brought to the outside of the motor so that I can make that adjustment externally. The same kind of a situation if the motor is a delta configuration, the windings are delta, and it's the same principle. I can divide 480 between 2 coils or windings that are in series, or I can parallel them so that they each have 240. Now we're going to revisit transformers just a little bit. If you remember, the way a transformer works is that we run current in the primary winding, and that creates lines of flux. And those lines of flux, in turn, cut the secondary windings, inducing a voltage. So E1 is the voltage in the primary, E2 is the induced voltage of the secondary. And we also learned that the ratio between the primary windings and the secondary windings determine whether or not these are step-up transformers or step-down transformers, and by how much the stepping is. There's also unity transformers that have a one-to-one relationship. They're specialized and they're used for isolation transformers, but we won't talk too much about those either. So the transformation ratio is defined by the ratio of the number of windings in the primary in 1 compared to the number of windings in the secondary in 2, which is also happens to be the same relationship of this voltage that we apply and this voltage that's induced. And whichever windings whichever side has the most windings, it's also going to have the most voltage. If I have more windings on this side than this side, then that means that this is a step-up transformer because it would have more voltage on this side. So V1 and V2 is the same as E1 and E2. The current, though, is going to be inverse. Why? Because in a transformer, the power is the same on both sides. The power is the same on both sides. So if there's 500 watts on the primary, there's 500 watts on the secondary, no matter if it's a step up or step down transformer. So think about it. Power is equal to V times I. So if in the case of a step up transformer and my voltage doubled, in order to multiply voltage by current, and my voltage is now doubled, my current has to be half what it was so that when I multiply it, it comes out to the same power that it was over here. And that's how a transformer works. It's a transformation of the ratio of power. Let's take a look at this example here. I have a power supply of 150 volts. My transformation ratio is 2.5, and I have a load of 2.2 kiloohms. And what I'm trying to find out is what is the current in the primary. I need to know that so I can, if I know what my load is, I need to know what my current is here so I can put the proper protection on it, breaker or fuse. Well, I'm going to have to figure that out. The first thing I'm going to do is figure out what this voltage is over here, V2. Well, I can find that out because I know that 2.5, the transformation ratio, is equal to this voltage compared to this voltage. So that's going to be 2.5 is equal to 150 over E2 or V2. So now I solve for E2 by dividing 150 by 2.5, and I get 60 volts. Now that I have that, I can calculate the current that's over here. So I know that I2 is E2 divided by R, so I can calculate that to be 27.3 milliamps. All right. Now using the transformation ratio, that inverse relationship, I can use this formula and solve for I1, and I get 10.9 milliamps. In this case, I have a transformation ratio of 0.5. That means that there's more on this side than the other. So back here, we saw that we had a step-down transformer. This is going to be a step-up transformer because this number is less than 1. It means there's more windings on the bottom than on the top. And yeah, so 0.5, the transformation ratio is equal to this divided by this. We get that, and we get 300 volts. It went up by 2, which is the reciprocal of 1/2. So I can calculate the current now in the secondary the same way I did before. It's E2 divided by R, Ohm's law, and I get 136.4 milliamps. To get this, I can do this formula here for the transformation ratio, and I get that. And another way I could have done this, if you think about this, once I had this voltage and this current, I could have multiplied this voltage by this current, and I would have got the power in the secondary. And knowing that the power is the same in the secondary as in the primary, I could have taken this power, divided it by 150 volts, and that would have given me the current. So whichever way works best for you, that's the right way.